This is a serious problem, correct? Whereas if I write it in the non-blocking state, in the non-blocking case means I write it like this way. I use less than 0 to write it, less than equal to. The if else and all are remaining the same here. I write q naught less than equal to d and q less than equal to q naught. The order doesn't matter at all. Here the order doesn't matter. Whether I write q equal to q naught first and q naught equal to d next, or I write q naught equal to d first and q equal to q naught next, doesn't matter, because all the RHS will be evaluated first, then it will be assigned to LHS. So there will be two flops here. Irrespective of order, I will get two flops here. So always the moral of the story is use non-blocking for writing sequential circuits. Whenever you want to write a sequential circuit, you always go with non-blocking statement. When we are using blocking statement, we have to be very careful. Okay. Let us look at one more caveat with blocking statement. This is another interesting point. This will cause a synthesis simulation mismatch. It's going to be very, very interesting. Let's see. See, effectively, what is our aim? Let us write our aim here. Our aim is to create a circuit which looks like this. So A, B, C, this is our aim, to create this. Now, in the process of creating this, what did we do? Let us look at this. I created a edge called Q naught. This intermediate point is what I'm calling as Q naught. Okay. I have written always at star, so no problem. Upon any change in A, B, C, this always module will be evaluated, so there is no problem here. But the problem is going to be here. Let's see. I am assigning y equal to Q naught and C first. That means I'm going to assign y equal to Q naught and C. Then I am evaluating Q naught for A or B. That means the A or B evaluated in the previous case. See, when the always module was entered, Q naught is not evaluated. The Q naught value is old Q naught value. Here, the Q naught value is getting updated only here, correct? Only when this statement executes, Q naught value will get updated, correct? This statement has not got executed at all. That means ABC change happened and I'm entering into the code, and Q naught value is the old Q naught value. The old Q naught value is ANDed with C and I'm getting Y. So this will mimic a delay or flop, correct? If when I have a flop, I will always look at one stage before, correct? Yes or no? If I have a flop, think about this. If I have a flop, the value here is one cycle before value, correct? Because this value is the previous value. Whatever comes on Q is the previous value. It will look as if there is a flop here. But when you synthesize, there will be no flop. If I change the order, let me clear this, whatever I have written here. So that the code is visible. Okay. Now if I see here, my aim is to create a circuit which is like this, correct? Now look at the code here. This intermediate point is what is called Q naught. When the always block is entered, I am evaluating Q naught first. So A or B is computed first. So this Q naught is computed already. Next I am assigning Y equal to Q naught and C. That means the latest value of Q naught is used here. In simulation. Whereas when I synthesize both the codes, this code or this code, both will yield me the same circuit. This will be the circuit I will be seeing when I synthesize. So this will also lead to synthesis simulation mismatch, because here I will look at old value of Q naught, which is giving me an impression as if there is a flop in the circuit, which is delaying the value by one stage, one cycle or something. But that is not happening here. This is just because of the ordering in the blocking statement. This is because of the blocking statement. Whereas here I will see the latest value of Q naught because Q naught is written first, and then we assign it to Y. So here in both the cases the synthesis will yield this circuit, whereas simulation I will see a different behavior. So this also causes synthesis simulation mismatch issues. Now because of these type of issues, it becomes paramount importance to run the GLS on the netlist and match the expectation of the it is very important to check the behavior of the circuit obtained and then match that with the expected outputs or the expectations which was seen in the simulation, and see that there are no synthesis and simulation mismatches, and that is why we run GLS. So we will do subsequent lab exercises exhaustively to run GLS, how to set up GLS, how to run GLS, and then see all these things in action. Okay, thank you.